Welcome to monochemistry. Today we're going to look at Arrhenius acids and bases, which is the first, most simplistic definition of acids and bases, and it was developed by a chemist named Arrhenius, hence the name Arrhenius acids and bases. And what you're looking at here is a picture of vinegar which is of course an acid. As you can see in the picture there, it says acetic acid. Right here. Now these guys here you've probably seen before or used before. They're litmus paper, and you can see the blue and the red litmus paper. And that picture is meant to kind of segue into a refresher on the properties of acids and bases. So let's take a look at those. You probably already have these properties in your notes, but if you don't, this would be a good opportunity to get them in. So there's different properties of acids and bases, and in general, although I wouldn't always recommend tasting everything you find to see if it's sour or bitter, the taste of an acid is sour and the taste of a base is bitter. Both of these substances will conduct electricity when they're dissolved in water. And bases tend to have a slippery feel when dissolved in water, whereas acids, you can't really tell. You just feel other than perhaps the intense burning sensation from the acid, if it's a strong acid. But realistically, the bases are the ones that feel slippery. Acids don't really have a distinct feel to them other than the water. The reaction with litmus, as you know, acids turn blue litmus paper red, and bases turn red litmus paper blue, and that's essentially the litmus test. I've heard that term before. Now, in the next couple of ones, we're talking about reactions with particular compounds. In the first one, we're talking about reactions with active metals. Active metals would include the group 2 metals, mostly. Group 1 metals, of course, but they're very hard to come by. So group 2 metals generally is what we're talking about. And essentially, acids will produce hydrogen gas, whereas bases don't do anything with those particular metals. Carbonate compounds with acids will produce carbon dioxide gas as part of the neutralization reaction, whereas bases don't react at all with carbonate compounds. When they react with each other, they neutralize each other, and at the bottom you see a general reaction that involves a generic acid and a generic base. So HA is a generic acid. A obviously doesn't exist. And BOH, B is the generic base. The OH fits in with the Arrhenius definition, which we're going to talk about in the next slide. And you can see what you get. Water, and this here, the BA part, which is, by the way, a double displacement reaction as well as a neutralization reaction, is some salt. Okay, so water and salt is what you get when you react acids with bases. Well, there's the handsome devil there, Arrhenius, who came up with the very first, most simplistic, or basic, pun intended, definition of acids and bases. And his definition basically states that an acid is a substance that dissociates in water to produce H+ ions. Okay, that again, an acid is a substance that dissociates in water to create or produce H+ ions. That's what it is. So any substance that when dissolved in water and produces H+ ions is technically an Arrhenius acid. Bases, on the other hand, are substances that when they dissociate form OH- or hydroxide ions. Okay, so a base is a substance that when dissociates in water it produces OH- or hydroxide ions. Right? And that is essentially the definitions that he came up with. Now, why I say that these are the most simplistic definitions, or basic if you prefer, is because they have limitations. And we're going to talk about those limitations on the next page. So the limitations of the Arrhenius model are as follows. First of all, when acids dissolve in water, like in this picture here, you can see what the dissociation equation would look like. So HCl, hydrochloric acid, plus water would give you H plus Cl minus plus H2O, right? Well, not exactly. We can represent it that way, but in reality, because water molecules are polar, the water molecules and the H plus ions, which are essentially just protons, stick together to form a compound called hydronium ion, H3O plus. And because of that, technically, is there any H plus in solution? And therefore, does Arrhenius' definition actually make sense? And the answer, of course, is no. So because of the complexity of the molecules and their interaction with each other in solution, the Arrhenius model starts to break down a little. There's another problem, too. For instance, you've probably heard that ammonia, when dissolved in water, equals a base. But remember, according to Arrhenius' definition, in order for a substance to be a base, it has to produce OH minus ions, or hydroxide ions, in solution. How does this produce OH minus? How can this be? NH3 doesn't have any OH minuses. So in reality, what happens is that the NH3 and the H2O form a compound that looks like this, which is called ammonium hydroxide, which, as you can see, does have a hydroxide ion. Unfortunately, Arrhenius' model doesn't account for those things, and therefore we say that it has limitations. The next model, the Bronsted-Lowry model that we'll talk about, deals with some of those limitations and increases our understanding of acids and bases. That, in a nutshell, is the Arrhenius model of acids and bases. Make sure you watch the video closely and take some good notes on this, and bring any questions you have to class. Take care.